Alright, so this is another titration problem, and if you're following along from your book, this is problem number 2 from page 80B. And again, remember the goal of a titration is to determine the concentration of an acid or base by measuring how much either base or acid is required to neutralize it. And in this example is a little bit different from our earlier example, because in this case, our unknown that is down here in the flask is sodium hydroxide. So we have a base down here, and we have 10 milliliters of the base, and we do not know the concentration of it, so that's our unknown. In our burette, we have an acid, and we know the concentration of the acid. It's 0.1 molar, and we know from our burette readings that the initial volume of acid in the burette, the initial reading, is 5.30 mils, and after you have added enough acid to neutralize your base, my final reading is 12.50 mils. If we're using the indicator of phenolphthalein, in this case we'd be looking from the for the phenolphthalein to start pink and to turn clear. This would be the opposite of what we were doing before. So, first thing I want to do is my balanced chemical equation. And the chemical equation, I'm going to figure out what I'm mixing together. So I'm mixing together HCl is the acid, and I'm going to be combining it with NaOH, the base. And this is a double displacement reaction. The sodium and the hydrogen are going to switch places. That gives me NaCl and H2O. Notice how this is salt water, so this will be neutral. And make sure you always double check charges. Sodium has a charge of +1, chlorine has a charge of -1, so no subscripts needed. Same for water. Water will just be H2O. Notice I don't need any coefficients, so it's all 1:1:1 ratios. Alright, the next step is to find moles of the known. So again, our known in this case is the acid. I know the concentration of acid, and I know how much volume I added. So to find moles, using my molarity triangle, to find moles I'm going to take molarity times volume. So my molarity of the acid is 0.100 molar. The volume of the acid that I added, you have to figure that out by doing a little bit of subtraction. So my final volume was 12.5 mils. My initial reading on the burette was 5.3 mils. So what that means is during the neutralization, I added 7.2 mils of HCl. And the concentration there was 0.1 molar, so 0.00. So to find the moles, I would take my molarity times my liters, so 0.0072 liters, and that will give me 0.00072 moles of HCl. So that's how much HCl was added to your flask during the reaction. Then you want to take your moles of known and use it to find moles of unknown using this mole ratio right here in the balanced chemical equation. So I've got 0.00072 moles of HCl. And if we think about this, this is a stoichiometry problem, so think about what we do in stoichiometry. We take half times 1 over half, and we use our mole ratio from the balanced chemical equation. So this chemical equation tells me that since there's no coefficients here, that means that it takes 1 HCl for every 1 NaOH to make 1 NaCl and 1 water. So it is a 1:1 ratio, 1 HCl for every 1 NaOH. So if I have 0.00072 moles of HCl, that means there must have been 0.00072 moles of NaOH down there in my flask, in my unknown. The last step is to find the molarity of your unknown, again using your molarity triangle. So molarity is moles divided by liters. So to find my molarity, I'm going to take my moles of base, just 0.00072 moles, divided by my volume of base, which is 10 milliliters, divided by 1,000 gives me 0.010 liters. So 0.00072 divided by 0.01 gives me 0.072 molar solution. So that is the concentration of my base in this example. And again, this is opposite of what we did last time. Instead of titrating an acid with a base, I'm titrating a base with an acid, and you could do it either way. It's the same idea. You're just saying how much stuff does it take to neutralize whatever my unknown is.